Hello, and welcome back. Today I will be showing the first table to be introduced into the Runtime Database, as well as the mechanisms for producing and consuming the data. At a high level, the table resources are protected by an RCU for synchronization, and reading and writing is done through a combination of push and pull requests. These push and pull requests have specific function signatures, and reading has two signatures. The first signature for reading takes the function and processes all the data in place, whereas the second takes the function and stores a local copy, and that copy is processed outside of the table. You work with a snapshot, essentially, of what the table looked like. Tables, and by extension the RCU, only accept a single unregistered writer at any time. For reading, however, any amount of readers are allowed, given that they are registered to the RCU. When a reader registers to the RCU, they are given a registration index which is used for updating a read flag which blocks out the writer from removing the currently read generation. The actual specifics of the RCU itself almost warrant its own video, so in a part 2 to this I will be diving into the specific implementation details of the tables and RCUs. In addition to the runtime database, a communication system will also be introduced. The communication system takes the usual responsibility of decoupling unrelated systems from their shared data. The system itself is an augmented form of the observer pattern. Currently, the system is used to load and notify the rendering and simulation systems when the binary database is loaded. These systems then process their respective data. Like the RCU, the communication system will be gone over in a part 2 to this video. Before actually loading the binary database and beginning to process the data, some registration has to be done. During initialization, the subsystem observers register themselves with observation tokens into event spaces. These event spaces are predefined actions which, when performed, generate an event which is distributed to the event space. The event space will then notify the observers of their particular observed messages depending on the tokens. Also, as previously stated, database table readers must also register to their table's RCU. The reader must store their registration ID as is used as an index into their reserved slot, and this will be shown a little later with the rendering of the states out of the node state table. After initialization and registering is finished, the binary database is loaded. In this particular case, the database is describing a scene, but that is not a requirement. However, to load the scene, the file system is given the path and the corresponding event space which the subsystem observers previously registered to. Since we can know beforehand what data and its format we are expecting, the load can be made rather trivial. For every binary record in the binary table, the data is stored as a message for an observer who knows how to process it. Messages also store a message type, which is used in conjunction with observation tokens for passing information through the event space. These messages are accumulated into an entire event, in this case called a file system event, but this is just a naming convention and does not actually change the event type. After all the event messages have been generated, the event space is notified of the event itself. And this can actually be disregarded, as you just saw. I ended up going with the staged init approach. However, nothing too much more interesting really happens past this point in terms of the observer. They just simply store the messages for the actual subsystem to do the processing, which I will go ahead and show now. When the subsystem updates, it attempts to process any events its event space observer may have observed. The specifics of what happens with the observed data is also known beforehand, so likewise they are wrapped up into their own processing functions. Starting with the physics processing function and skipping down to where the message handling portion is, we see that the geometry node is pulled out of the message and transformed into a runtime object. In this case, that object happens to be a rigid body. The body data is then added into the physics system for simulation. Once each message has been processed, the physics system itself actually triggers an event, and this event is in the graphics system, which we will see in a moment. One thing that should be mentioned is the nodes are being shared between the physics and the graphics, but they go through the physics first to make sure that a body and a corresponding state can be created for that node. The graphics is only really interested in a node instance when it has some renderable state it can apply to that node. The actual shared data between the node, the simulation, and the renderer is going to be this ID right here. The graphics system currently has two observers it works with, one for the file system and one for the graphics itself. The file system observer has its messages processed in a similar fashion to the physics, but instead of creating rigid bodies, they're instead creating materials, meshes, etc. Then in the graphics processing function, new nodes are received and they're also added into the graphics resources, but now they act as a nexus point between the previously loaded meshes and materials and all that. Without these nodes, the graphics resources would just sit idle. Now that everything has been loaded into the game, we can begin producing the state which the renderer will consume to render its nodes. Here we see the aforementioned write function signature for pushing data into the database. The write function simply returns a T star, which is noted by the table itself, or determined by the table itself, and then a variadic set of parameters. When the table is open for writing, the writer locks the table and calls its write function. Specifically in this case, we are going to integrate our bodies. This integration will produce a snapshot of the node state which will be uploaded into the database. Here at the beginning of the function call, we create a buffer to store the data, and then at the end of the actual integrate function, the current and previous orientations and positions are stored alongside their respective node IDs. The results of this are then pushed into the table, where they are written into a new generation handle, and the writer waits for old readers to finish the previous generation, or the previous, in this case, state read, and then when that is done, it releases the unused memory and sets this generation to null pointer. And now we pair our previous push with a pull. And in this case, we'll be using the second read signature, which is the read copy function. And in this case, this is done because as the number of actual nodes in the simulation grow, the amount of time spent processing state informations during the graphics pipeline may unnecessarily block writers. However, in either case, the bones of pulling are the same. We get a handle to a specific generation, in this case a generation of state data. While that handle is owned, you are guaranteed that the simulation cannot invalidate the states you are currently reading. Then once the snapshot of the states has been taken, you can unlock for the writer to begin pushing new states into the table. And just for completion's sake, I will show what that state data is used for. A scene graph is built up of each node, and to reduce driver overhead, the graph uses different instances of objects as the primary segregator of data. So each object is a node in the scene graph. Then for each of these objects, or each of these nodes, it has a list of which objects are using what materials, or which instances of this object, the states and their node IDs. Which materials are they using to render the mesh that is associated with this object. Once that graph has been built and each node has its corresponding state and matching mesh and texture IDs, the graph is traversed first by object, then by material instance, binding the textures and objects each along the way, and then finally we set the model and render the actual mesh instance from the node. And now if we put all of that together, we get something that looks like this whenever this loads. And there we have it. And just to recap where this data is coming from, it came originally from this GEX file, which was turned into the binary database and then loaded in as a scene. And we can see here is our green cube. This will be our first blue cube. This will be probably this red cube right here. This is this red cube. And then way in the back is this final blue cube. So thank you guys. In the next one, I will actually go into more detail about uh, the design and the reason behind that for the communications and the actual implementation details for the RCU and what it is going to ultimately be used for. I mean, it's pretty obvious, but the reason why the registration is done the way it is to allow it to integrate better with the thread pool. But like I said, I'll go over this in the next one. Thank you for your time, and I hope you have a good rest of your day.